Pruning. Frequently, a node is not split further if the number of training instances reaching a node is smaller than a certain percentage of the training set, for example 5%. Regardless of the impurity or error, the idea is that any decision based on too few instances causes variance and thus generalization error, stopping tree construction. Early on before it is full is called pre-pruning the tree. Another possibility to get simpler trees is post-pruning, which is in practice works better than pre-pruning. We saw before the tree growing is greedy, and at each step we make a decision, namely generate a decision node, and continue further on, never backtracking and trying out an alternative. The only exception is post-pruning, where we try to find and prune unnecessary subtrees. In a post-pruning, we grow the tree full until all leaves are pure and we have no training error. We then find subtrees that cause overfitting and we prune them. From the initial labeled set, we set aside a pruning set, unused during training. For each subtree, we replace it with a leaf node, labeled with the training instances covered by the subtree, appropriately for classification or regression. If the leaf node does not perform worse than the subtree on the pruning set, we prune the subtree and keep the leaf node because the additional complexity of the subtree is not justified. Otherwise, we keep the subtree. For example, in the third tree of figure 9.5, there is a subtree starting with a condition x less than 6.31. This subtree can be replaced by a leaf node of y equals to 0.9, as in the second tree, if the error on the pruning set does not increase during the substitution. Note that the pruning set should not be confused with and is distinct from the validation set. Comparing pre-pruning and post-pruning, we can say that pre-pruning is faster, but post-pruning generally leads to more accurate trees. Figure 9.5 Regression trees implementing the smoothness of figure 9.4 for various values of theta r. Figure 9.6 is an example of a hypothetical decision tree. Each path from the root to a leaf can be written down as a conjunctive rule composed of conditions defined by the decision nodes on the path.